The broadcast is now starting. All attendees are in listen-only mode.
Good morning and welcome to the science behind today's milling materials. My name is Candace and I'll be facilitating today's webinar. I'd like to begin with a few housekeeping items. First, in the upper right-hand corner of your screen, you should see a questions box. Please feel free to type in any questions you may have throughout the presentation. We'll be answering all questions at the end of the webinar. The course is NBC approved for 1 credit. Within 48 hours, you will receive information on how to obtain that credit. We will also be posting the webinar on our website in case you miss any portion or would like a review. I'd like to introduce our presenter, Brian Knopf. Brian has over 20 years experience in research and development in the aerospace and dental industries. He has a Bachelor in Science and Chemistry and a Master's in Business Administration. Brian is Vice President of Technical Services at Whitmix Corporation, where he oversees the Research and Development, Engineering, and Quality Control departments. I'm going to hand it over to you, Brian.
Okay, thank you, Candace. And thanks, everybody, for joining us today. Welcome to our seminar on science behind the CAD/CAM materials. I'm sure all of you, like us here at Whitmix, are aware that there have been a number of changes here, especially due to CAD/CAM. As you can see on my screen, this is an example of CAD/CAM milling, and you know, it's really having an impact. You know, in the past, we're familiar with handcrafted dental restorations via the lost wax technique, and that's all changing. And within those changes are not only new equipment or processes, but new materials. And these materials behave differently. So that's what we're really going to cover today. Our agenda is a basic overview on the science behind several of the key materials, and then tips and techniques. Okay, how do you use these? And I'm really working off the premise that most people are familiar with PFMs, and so they're accustomed to working with metals or porcelain, and so really, what is different? All right, so today we're going to talk about millable zirconia, and really this is going to get the lion's share of the discussion. Also, I'll talk about millable pattern wax, millable PMMA or related polymers. I kind of use PMMA as a generic term. Other millable medical devices, so other products. And as I'm talking today about these new materials or these different materials, in addition to picking up, you know, some ideas on the science and how they may behave differently, or the tricks that make them work, is also what are new opportunities. So as we mentioned, things are changing. Will there always be a need for a handcrafted PFM? Probably, but CAD/CAM really is going to have a major impact. And so as we go through today, is to also kind of think or see if you get any ideas on new opportunities. You know, here's a new product or a service that I can provide now that I can take advantage of CAD/CAM to make restorations. All right, so millable zirconia. I guess I first heard of it as cubic zirconia as the ring. And when we talk about zirconia, we're going to see it really covers a range. So it starts with cubic zirconia. This is a form of zirconia. Zirconia, because it has really unique properties that we're going to talk about today, is used a lot in industry. Because of its strength, its abrasion resistance, etc., they're using it more and more for industrial applications. Professionally, I became aware of zirconia. In my past life, I worked for a firm that made investment castings for aerospace, but they also, maybe about 10% of their business was medical devices, and they made the hips and knees, etc. And so we would make that metal component you see, and then it would be sent out to have the zirconia plated on the surface. And early on, there were some real learnings related to using zirconia in biomedical. We'll talk about that a little more later. And this, of course, is what we're all interested in, is zirconia to make teeth. So we see here a 4-unit bridge, and I want to emphasize that, again, that zirconia is very strong. Though if you look at this, it's not necessarily all that translucent and maybe all that natural looking. This is a case of a PFM. Now, if you use zirconia as your substrate and apply porcelain on top, again, you can get beautiful restorations. Though, again, zirconia by itself is a little more opaque, not quite as translucent as you can get with a good porcelain. But again, this stuff is strong. We could take this 4-unit bridge that you see, we could take it out to our shop, run over it with a forklift, and it wouldn't have any negative impact. Now, why is it used more, or why hasn't it been used more in the past? Well, it is so strong. It's very hard to machine. Goes through tools like crazy. So in its centered hard state, it's very strong but very hard to work with. But the other is, in its green state, or what we call pre-centered state, it's also hard to work with because of the shrinkage. And if you look, you see this is the green or pre-centered state, and this is after firing. Significant shrinkage, depending on the density, 22 to 25% shrinkage. So this is significant and nothing that you could really control by hand. Well, but for CAD-CAM, it's a piece of cake. So for CAD-CAM, you just dial in that shrinkage factor. So the manufacturer, when they make the zirconia disc, they've calculated the density, or determined the density and calculated that shrinkage factor, and they're going to provide that for you. So again, we're talking mostly about zirconia, and I'd like to start with nomenclature. It's amazing how many people say it wrong, including myself. What we're talking about is zirconia. Okay, it's an oxide of zirconium, which we'll see here in a second, is an element, atomic number 40. It's a metal. It's kind of like titanium. So zirconium is a metal that's been oxidized to form zirconia. So when you hear somebody saying, yeah, we have a zirconium machine, they probably don't. I don't know of anybody milling pure zirconium. Or you may hear zircon. This is a zircon machine. Now, zircon's a different chemical. That's zirconium silicate. So zirconium oxide or zirconia. Sometimes I've heard people say zirconia oxide. Well, that's like saying zirconium oxide. All right, so zirconia, just to wear that out a little bit. But you'll also see it called YSZ, or yttria stabilized zirconia, or YTZP, which is yttria stabilized tetrahedral zirconia polycrystal. Wow, that's a mouthful for me. And I want to hit on that, or we're going to expand on that further, because it really, the magic is kind of based on this yttria stabilized tetrahedral zirconia polycrystal, or polycrystal formation. And so zirconia is a ceramic. It's an ionic ceramic, and in its form, again, it's zirconia and oxygen, and it forms a crystalline lattice where, in this case, pick one, the zirconia is the red and the oxygen's the white. It'll form this crystalline structure because the oxygen basically takes electrons away from the zirconia, leaving the zirconia with a very strong positive charge, while the oxygen ends up with a very strong negative charge. So you have these positive, negative charges balancing each other in this crystalline structure. So it's part of the strength of zirconia. These are very strong bonds. When we talk about yttria stabilization, we're actually adding another metal oxide, yttrium oxide, which we call yttria, into this matrix. And it actually disrupts it enough to where, as you'll see in a little bit, it gives it some special properties. But it's this structure that's really key that we're interested in. And I want to point out that porcelain, which you're, I think, primarily used to or familiar with, is really different. Though they're both technically ceramics, porcelain starts as crystalline minerals, and when it's heated, it basically melts and fuses into an amorphous, glassy substance. So porcelain is closer to glass. Actually, zirconia is not. Zirconia stays as a crystalline mineral. So I point this out because on the zirconia, we're not going up to a melting point where it now goes from solid, kind of this liquidy state, to fuse. It's going to stay like this its whole heating, sintering process time. So it really is different than porcelain. So later when we talk about how we have to treat it different, hopefully this will help and that'll make more sense. Okay, so when I talk about those crystals, let me back up a second. So when we talk about those crystals, the distance and the packing, they can take different packing orientations, and the configuration they're in is called an allotrope. And zirconia can form into 3 different crystal allotropes. So it can form in the monoclinic, and this is at room temperature. This is its normal, stable condition. So it 3-dimensionally has one structure, so there's a set distance between the atoms. There's a certain packing orientation between the atoms. As you heat it up, it can go to the tetragonal. And basically, the atoms are realigning and kind of scrunching in a little tighter. So when it's heated above 1170, we have this tighter configuration. And I don't know if it's obvious to you, but if you notice my font size from monoclinic to tetragonal to cubic gets smaller. All right. So as it's heated and takes on this other structural form or cubic form, that it's really kind of shrinking in size, getting denser. And then if you heat it further, you'll get to the cubic. That would be what we consider the cubic zirconia. Now with zirconia, I want to point out these little 2-way arrows. Okay. What that means is when I cool, it's going to step back through these. So as I cool below this 2370, it's going to go back to tetragonal. As I cool below the 1170, it's going to cool to the monoclinic. So its normal mode for pure zirconia is to exist in the monoclinic phase at room temperature. Now, that's kind of unique to zirconia in a sense that if you think of carbon or graphite heated up to diamond, that's very stable. So it would really be a one-way arrow. But unlike that, excuse me, I had a blinker on my phone here. Unlike that, the zirconia pure will step back and try and retain that monoclinic condition. And you can imagine in doing that, it's actually expanding again, and pure zirconia will just kind of break itself apart. But there's some tricks, and that is with the addition of stabilizers such as yttria or yttrium oxide, you can get zirconia to exist in other phases at room temperature. All right. So if we load it with enough stabilizer, we can get all the way to the cubic zirconia that we see as that nice, beautiful diamond-like material. But if we dope a small amount, we can achieve this partially stabilized tetragonal phase. And I want to build on that tetragonal phase a little more. So we're talking about we have the 3 allotropes, and we're tricking it to stay in the tetragonal. But I also use that term partially stabilized. So it's here as a tetragonal, but it can be converted. So now maybe the names start to make a little more sense. We have yttria stabilized zirconia, or that yttria stabilized tetragonal zirconia polycrystal. All right, so we've stabilized it into this tetragonal structure. Now, the magic of zirconia, what makes it special, is the following. When it is stressed, so we have partially stabilized tetragonal zirconia. When a stress is applied, it'll convert to the monoclinic. Okay, it's going to go back from the tetragonal to the monoclinic with a subsequent increase in size. So let me show you this little model. Okay, so what we see is that as we applied a stress and it promoted a crack, that the tetragonal zirconia converted to monoclinic, increasing in size and basically plugging the crack. or to say it more officially, when a stress is applied, the metastable tetragonal phase converts to monoclinic. This puts the crack in the compression, retarding its growth. So this is the magic really behind zirconia and why it's become such a popular material for medical. All right. Some of its features are excellent fracture toughness. Again, we can drive over it, we can hammer nails with it. It's a very strong material. Low thermal conductivity diffusivity, and we're going to talk about that a little more in a moment, but it means that unlike some materials, it transfers heat very slowly. So if you had a full contour zirconia crown in your mouth, you're not going to be as sensitive to cold and heat as you would with maybe some other materials. Excellent wear resistance. Again, very strong material. Excellent impact resistance. You could take a zirconia abutment and hammer it into a board like a nail, and it's not going to crack. Good resistance to thermal shock. So if you think of glasses in the old days, I think they've pretty well adjusted that now. But if you cooled them too quickly, if you took a glass and put it in cool water, it would crack. Zirconia is not going to do that. You can go from very hot to very cold very quick without any detrimental effect. Excellent chemical resistance and corrosion resistance, and both of those are partly why it's so ideal for medical. It's just very stable material. Now, the concerns. Post-sintering process. Early on, there were a number of issues because labs and doctors tried to process it like they would a porcelain. So they grab their grinder and their burr and start cutting away to make the restoration fit. And that's a no-no for zirconia. You don't want to heat it. You need to use a water-cooled diamond burr. Think of when I showed that picture, that little model where we applied a stress and the tetragonal crystallites converted to the monoclinic. Well, that only happens once. It's like a match. Once it's lit, you can't light it again. And so once you've done that, you've already taken away the magic, so to say, from that part of the restoration. So you need to be careful in how you process it. The other is an issue called low temperature degradation. And when I showed those pictures of the hip components earlier, that was a big issue. I think it was in the early 80s where they had a number of failures after they were implanted in people. And what they found is that depending on the additives to stabilize the zirconia, is that even at room temperature or body temperature in a humid environment, some of that moisture would interact with the surface and actually convert some of the tetragonal to the monoclinic. And now if you get crystallites swelling at the surface, they're going to pop out and spall, and then it gets progressively worse. And they've addressed that mostly. You'll see that the zirconia used now for medical and dental has alumina in it, and that helps minimize the low temperature degradation. But I'm going to hit on this again because we'll see that in our processing we can also worsen this. Now, I do want to make a note that it depends on who you talk to how severe this is. If you talk to some of the experts, and especially the experts that went through that really a terrible time with failures in patients, are very sensitive to this issue. And when we look at the higher translucent brands of zirconia for dental, what they've done is they've reduced the amount of alumina. And so your experts are kind of concerned with that. But other experts point out that there haven't really been any device failures. When we're making a coping, we've got porcelain on one side and adhesive to the tooth on the other, so we really aren't exposed to moisture. And if we are making a full contour and we put the glaze on it, then again we've sealed the surface. So the feel is that if the surface is adequately coated and the zirconia was processed correctly, that really is a minimal risk. but I need to point that out. Other concerns are that thermal diffusivity. Man, that's tough for me to say, huh? This also was a problem early on in that when they started applying porcelain to zirconia, they were getting spalling, cracking, and a host of issues and problems. And so they thought, well, we need to make sure we match the coefficient of thermal expansion between the two, and they did, and it didn't help the problem. And then finally someone realized, hey, the difference is in that thermal diffusivity. Wow, sorry. Is that the zirconia cools slower. All right, so if they both shrink the same amount upon cooling, but one is cooling slower, then relative to the other, it's going to shrink faster. And that was the problem. So the porcelain, and you think of built on top of a coping, kind of like a crown, and if it's cooling faster than the coping below it, then it really kind of cracked upon itself. It created a force upon itself. So it's an easy fix. You just don't cool as fast. So you should have, when you're using a porcelain for zirconia, they should have instructions on what that cool rate is to minimize that kind of issue. The other problem is over-centering, and I'm going to talk about this further, but over-centering is centering is one of the process steps that you're going to do. A lot of the other properties of zirconia were impacted by the manufacturer or set in place by the manufacturer. But you are actually going to be centering. And so there are things you can do that is zirconia. Again, we're going to talk about that a little bit more in a bit. And all in all, again, this is a new material. It's not going to behave like porcelain or what you're familiar with. And so I strongly suggest following the manufacturer's instructions. They've been working with this material for a long time. They should have addressed all of the issues. And again, it's not like what you're used to. So do your homework and be prepared, and you'll minimize your problems. If you want to learn more about zirconia, then there's a number of resources. We got Dr. McLaren, Giordano, and Dr. Russell Giordano. He is really one of the leading U.S. experts. He is on the ADA ISO committee for developing standards. In fact, they are working on a new standard right now. I was able to join them a couple of weeks ago. And currently, the zirconia millable blocks fall under the standard, the testing for ceramics. And it really doesn't capture a lot of the issues, a lot of concerns like that low temperature degradation that are unique to zirconia. So the new standard will be much more tighter and more applicable to zirconia. But again, there's a number of resources, a lot of good material out there on zirconia if you want to read further. But I'd like to sticking with zirconia, I'd really like to go a little more on the material and use by the dental lab. So you've bought a milling system, you got a scanner and a milling system, and you have all the programs, the right programs in there, you have them dialed in, and you need to buy this zirconia disc. And I guess the question is, are all zirconia discs the same? And I'd say in theory, yeah, they're taking powder from a zirconia manufacturer, they're pressing it into a disc, they're pre-centering it to get it strong enough so that you can mill it, and providing a shrinkage factor. So in theory, you should be able to use any disc, but in reality, there's a lot of things that go into making that disc. And so I just want to make you aware of, here are some of the issues. So if you have problems, or if you see that, I can get this one disc from, when I was at that ADA meeting, they called it Joe Banana, but somebody that's just bought the equipment and qualified using the ceramic standard could be making zirconia, and it may not be what you need. All right, so here are some of the things I want you to be aware of. So if you're talking to your supplier, questions that you can ask them so you can get a better understanding and a feel if this is the right product for you. Because your end result can be no better than the zirconia disc you're using. And just a side note, one of my hobbies is roasting coffee. And, you know, for years and years and years, I drank the stuff in the can or in a coffee shop or a restaurant and you know, kind of lived with it and didn't realize how great coffee can taste when you brew and grind your own. But you can only get as good a product as the beans that you start with. If you have really poor beans, you can't get a good coffee. Well, same with zirconia. If you get a poor starting material, you can't produce a high-strength aesthetic restoration. So I just want to go over some of the nuances in making zirconia so that you're aware, again, to ask a supplier. How are they made? Well, they start with a formulated powder. And normally, it comes from a manufacturer or supplier in Japan called Toso. Most discs are made using Toso powder. And ask your supplier. I think that's a fair question. Are you using Toso? Some aren't. I know there's a source out of China, and I know a major player out of Europe uses that, so I presume it's a good source. You know, I'm not discrediting it. I think most of the suppliers of zirconia have found the problems early on. There's an issue with radioactivity because one of the isotopes that are found with zirconia in nature, I think it was thorium, has a low level of radioactivity. And so if you look at specs on zirconia, they still include a requirement for radioactivity, though I don't think that's really an issue anymore. But the quality of that powder is important. And you know, currently I think there's only a few providers, but down the road there may be more. You know, as people see this taking off, others may jump in. So just make sure that your discs are made from a reliable powder source. So the manufacturer now takes the powder, they form it into the disc. They call it coining, using an axial press. That's something like a 100-ton press that they'll use to form that powder into a disc shape. Next, they'll take that disc and put a group of them into a basket and load them into a cold isostatic press. And what this does is isostatically apply pressure all around, 360 degrees, with the intent that we're going to produce a very uniform density throughout that disc. Once they're sipped, the discs are pre-centered. And this is one of the most critical steps in the process. The discs are put into a furnace. We call it a bisque furnace. And they're slowly heated up to around 1,000 C, it's pretty warm, over a significant period of time. So we show 50 hours. And the reason is that there's a binder that helps hold the powder together during the pressing step. So we want to let that release slowly. If we let that release too fast, it can blow your discs apart. But the other is that we need to ensure that we get uniform heating throughout the discs in the oven and then throughout a given disc. So for example, if a disc was in the middle of the oven and it didn't get to the same temperature as on the outer, then it's going to have different properties. And even within a disc, if we went too quickly through that cycle, the outside of the disc may have heated up to the 1,000, but it may have been a lower temperature inside. Well, now we have different densities. So this pre-centering step is very critical. And then the discs are machined to their final dimensions, and that's usually just putting that collar in, and the shrinkage factor is determined. So really what they do is they measure and weigh the disc, determine the density, and they know the theoretical density for the zirconia and come up with a calculation. And again, it's amazing how accurate that is. With that, 22 to 25% shrinkage is significant, and yet you can get that in, dial that in within microns. You can be very accurate if your density is uniform throughout your disc. So this above process affects purity contamination. So if a disc isn't made in a very clean environment and they pick up something, that can get transferred, and you may not see it until that part is actually centered. This is one of the learnings a lot of the disc manufacturers have found, is that if they have any source of contamination, again, they may not see it until the end result, which is the customer centering the final restoration. Flexural strength, how it's pressed, and even though you're going to center after these discs are made, if your density isn't uniform throughout, or you really don't have enough press there, it's going to affect its final centering properties, and thus like the flexural strength. Could greatly impact the density or that shrinkage uniformity. So if when you're pressing that disc, that first is that axial press, and you're actually pressing in two directions, and so you can actually end up in a situation where you do not have uniform density in all three axes. You may have greater density in two axes than the third. That's why a lot of companies had started out just using the axial press, and they've shifted to also sipping. So that would be a question too, is to ask, are they sipping as well as pressing? And I think most companies have by now. But that density shrinkage uniformity is really critical, and in the new standard that they're developing for zirconia, one of the steps is to section thin little strips of zirconia and fire those, because if the density isn't uniform throughout, then when they're fired, they'll warp. So that would be one of the tests in the future to ensure. And why is that important to you? Well, if you've got a 8-unit bridge or a large appliance, or even an abutment, custom abutment that you've made, and you fired it and now it's warped, you've lost all that time and effort. So uniformity is critical. Thickness uniformity, I think most companies do well here. You come in different thicknesses on your discs, so from anywhere from 12 millimeters up to 20-some millimeters, and you plug in a number in your mill that says what is the thickness of the block, so it knows where to bring the tool to. Sometimes blocks are non-uniform, and you may end up with a thick end or what, and your tool hits it too quickly and it can damage the tool. But most quality manufacturers have uniform thickness. And again, not to be critical, but there are a lot of manufacturers now on zirconia discs, and a lot of these players come out of, because I was talking to Tosel, and they wouldn't give me names, but who are the key players in dental? Are they dental companies? And he said, yeah, some are dental, but a lot of them are the industrial ceramic companies that they have the equipment and they see the need, so now they're also making zirconia discs for dental. So hopefully they've got a clean room or a cleaner room, and they're not doing that out there in their general production areas. Let's see, the way the disc is processed can affect the milling properties, and partly is if it changes in density. In that pre-centering step, if you underfire, you can be too soft. If you overfire, you can be too brittle, and that'll affect your cutting speeds and your chipping. And then lastly, color and translucency. And where you really see this is on that, again, that pre-centering. If you don't do it right and don't do it consistently, then a lot of the coloring that you do on the zirconia is in that green state before you center it. And so if you dip it and that restoration that you just milled is too dense, it won't absorb the color. Or sometimes it may absorb it and sometimes it won't. So it's really important when you're looking at your zirconia disc manufacturer, try different ones and find the one that works best in your operation. The other thing I'd mentioned earlier, or the big thing that's under your control, is the centering process. So just to go over what's happening. So if this were porcelain, actually what we would see are crystalline particles that as we heat up, they kind of merge and melt together into this amorphous matrix. Well, that's not the case with zirconia. These are the particles, and within these particles are zirconia crystallites, and they're already in the tetragonal, the stabilized tetragonal form. When you heat it, you are not converting it from the monoclinic to the tetragonal. Okay, it's already in the tetragonal form. The powder manufacturer doped it and got it into that form. So these are just powder particles of the tetragonal zirconia, extreme stabilized. Now we've packed them so they're very close together and near touching. And as I said, there's usually a binder in there that keeps them together. When we pre-center, they start to merge together. Again, it's not melting. It's called solid state diffusion. So in a solid state, they're hot enough, and the molecules are vibrating fast enough that they actually start merging together. And then as we fully center, all of the material that wants to form together, wants to minimize the surface area, that's the energy that's driving this, and all the voids are working to the surface. Okay, so via the solid state diffusion, the zirconia, tetragonal zirconia stabilized particles merge together, the voids work out, and we end up with a solid. So under firing can leave voids, and over firing can cause excessive grain growth and separation of stabilizing agents. So in the end, we're creating these little crystallites. And within these crystallites are the stabilizing agents, the yttria, the alumina, and I think cesium is another one. So they have a number of different chemicals in there that help maintain that tetragonal phase. If you overheat it, these grains tend to grow, which isn't a good thing. Now it's kind of like you're asking too much of your additives. You're trying to get them to control a bigger and bigger area, a bigger volume. The other is if you overfire, some of the additives can start migrating together and kind of precipitating out. And when I say overfire, it's not just temperature, it's also time. So your manufacturer of that zirconia has specified a time and temperature that's ideal for that material, and follow that. And the reason this has become an issue is we've had a number of folks that, because I guess in porcelain, and I'm not a porcelain expert, but in porcelain, sometimes if you overfire it a little bit, it'll help your translucency. And that really isn't the case with zirconia. It's really not melting. And actually, okay, so you have a couple grades. You've got one grade for copings. It's very opaque, and you don't worry about it. People don't try to overfire that. But the other grade for translucency, they want to get the translucency of porcelain, and to be honest, it just doesn't happen with zirconia. Zirconia isn't that translucent. And a lot of folks think, well, if I overfire, it'll get there. And actually, you overfire, you'll get kind of this glassy look, and some people may think that means it's more translucent. But if you've got that far, you've greatly destabilized your product. It's going to be very sensitive to that low temperature degradation. You'll have killed the strength in half. So again, be wary of overfiring. If you're not getting the translucency you need, and there's been cases where we've gone through the centering and we end up with it's a translucent grade, a solid white chiclet, and it's like, whoa, what happened here? Well, it wasn't the firing, and it wasn't necessarily the zirconia. We had a contaminant in the process. So that's the other, is as you're centering, is make sure you have a clean process, that your furnace is clean, and you're not adding any contaminants. So recommendations on zirconia is, again, purchase your disc from a reliable source. It's a significant investment. This is your consumable, and price is important, but quality's got to be number one. All right. So, and I think it's fair to question your supplier, and if your supplier doesn't have any idea really where they're made, what they're made of, how they're made, then you may want to talk to somebody else. The other is, again, as a manufacturer, I always harp on this, is follow manufacturer's instructions precisely. As a consumer, I'm as bad about this as anybody else. You know, I'm a typical American. I just jump in with and try and make things happen. But since this is new and really these materials are different, I'd strongly suggest looking at the manufacturer's instructions. And again, my big thing is don't overfire. You can just do so much damage to a really good product. Okay, well, let's shift gears here now, and let's talk about millable waxes. And these are really for patterns. The classic wax that you're using now for hand waxing is really a combination of paraffin, microcrystalline wax, candela, carnauba, beeswax. These are all kind of natural, organic-y type waxes. Some can be from distillation or petroleum byproducts, but they're fairly low melting and typical of what I think of what would be used in making candles. And that's kind of what most waxes are. There may be some more plasticky type ingredients in there, but in general, they're candle wax type compounds. And so, again, chemically, since this is material science, these waxes are classic chemical compounds that are plastic, which means malleable, near ambient temperatures. They typically melt above 45 C or 113 to give a low viscosity liquid. So you can pop these into your wax pot. You really don't have to dial it up that high to make them work. They're easy to work with. Again, soft. They trim very well. They're really nice. Well, the millable are a little different, and chemically they're really similar. They're just more so, in that if you looked at the chain length and the complexity of the hydrocarbon chains in your classical dental wax, they're simpler and shorter. Where on the millable wax, even though they have names like polyethylene and polyvinyl acetate, they're really just longer chains and more branched. And they may have some special groups in there, but in general, they behave kind of the same. But because they're longer, they really increase that melting point. Polyethylene, which is usually a key ingredient in the millable waxes, is a thermoplastic polymer, so on heating it'll melt, just like your candle wax. But again, it has much longer hydrocarbon chains and typically more branches. There's a number of different grades that are used, and compared to your other waxes, you can see they have a much higher melting point. Instead of 45 C, you're up at 120, 130 C, or 248 to 266 F. So what should you expect to see when you're working with it? Well, again, they have the higher melting point. So if you're using a wax pot if you want to, you can actually remelt this stuff. So if you're cutting patterns and you've got some scrap, you can remelt it, but it's going to be at a lot higher temperature. And you're probably going to have your tools that you're working with, your waxing tools, hotter. But one of our technicians that used to work here, I gave him samples of wax, and he said, yeah, they're a little different, but you just adopt to it. But so I think if you're aware that, hey, if these millable waxes, I've got to treat them a little differently, forewarned is forearmed. They're much more viscous, and so at melt, a regular wax is going to be much more fluid, where these are pretty thick. And with that is, you'll notice what I call stringers. So if you're trying to, with a hot tool, work the millable wax, you may notice that as you pull your tool away, you get a stringer. That's pretty normal. Rob, the guy, our technician that I worked with, he had a technique where by hand he could minimize or eliminate that just in the way he handled his waxing tool. But be aware that could happen. And if you're the lab owner or the lab supervisor, I think you really need to let your waxers know up front that this stuff's going to be different. Otherwise, they're going to fill that and be uncertain. The others that won't carve as easy. It's a little tougher material. Still carvable, but not as easy as your classic wax. Now, on the other hand, it's much stronger than normal wax. It has less dimensional deformation. You know, it's very stable material, and it has similar casting properties. I know in the old days, some of the sprues and other components you could get pre-made out of plastic sometimes caused an issue, but those were a different type of plastic. So these millable waxes, even though you kind of call them plastic because they're polyethylene, they still behave a lot like a common wax. And so we did castings with conventional wax and millable wax, and we have a real standard process, and we have dies that we cast and can measure. And so we noticed that we didn't get quite as much expansion with the millable wax as a conventional wax. Now, I've talked to a number of lab people that are using CAD/CAM, and they've never noticed a difference. But for us, under our controlled environment, we could see that. So, you know, what we would do is if we wanted to compensate, we could increase the liquid concentration. Okay, the other material that's often used for patterns, especially large multi-unit bridges where flex and warpage is an issue, is polymethyl methacrylate. PMMA is a transparent thermoplastic. It's often used in lightweight or shatter-resistant glass, also known as bulletproof glass. Chemically is a synthetic polymer of methyl methacrylate, and you know that as denture material. And I think a lot of people started with this because it was a dental material, but there are actually better materials for milling out there. Yeah. And so if you, I kind of treat this generically. This is part of a polymer family. They're called acryls, and they all share similar functions groups here. It's just how they're branched and what other chemicals are part of this. But there's a number of other materials that you could look at. So if you want something that's stronger, you can by all means use the PMMA, but there are a number of other materials that will do as well or better actually. But uses are long spans, tri-ends. Now, when you look at a tri-end, make sure that whatever brand of PMMA you got has a FDA 510K approval. Because if it's going in the mouth, that's different than if it's a pattern. Same way with temporary restorations. Let me hit on that a little bit in a moment. So here's an example of making up an 8-unit bridge with PMMA. Very strong, very stable. Now, we found in our lab, if we were using this as a pattern material, that we didn't get near as much expansion. In fact, we actually saw a net shrinkage. So before, when I showed conventional wax and millable wax, they were at least both positive, where the PMMA, we got a negative. Now, I've talked to some labs, and they've never seen this issue, so I don't know I don't know why. But what we found we could do is, since we were making the patterns by CAD/CAM, we could actually dial in a correction factor like you do on the zirconia. You put in that shrinkage. Well, here we could put in that shrinkage factor, and we could get great fit. So that's an option if you're using PMMA or really any of these other materials and you're not getting your fit. You've got that correction factor like you do for zirconia that you can compensate. So something to be aware of. Other materials, so temporaries has really started evolving. In the past, I don't think this was something that it was easy for a lab to provide. It really, you know, it's not practical to work with PMMA as it is, or some of these others. But now that you have CAD/CAM, that gives you a new offering that you can provide back to your chemist or back to your dentist. And in a lot of cases, it's not practical for the lab to produce the temporary. It's easier to do that chairside. But in cases, especially implants or where they need a longer-term temporary, that may be something that you can look at and provide. So a lot of them are made from PMMA or these acryl polymers. There's going to be more and more of them out there. They're available in multiple tooth shades. I think we are going to be seeing better milling and better lasting materials in the future. Again, I don't think PMMA is one of the best for milling, but now that it's starting to move and there's getting to be some volume in sales here, I think you'll see a lot of other manufacturers finding better materials to fit this niche. But again, a warning that anything that's going in the mouth, and I'm sure you know this, but it has to be FDA 510K approved. And part of the reason I say that, there's a lot of PMMA blanks out there, and a lot of them that are even too shaded, but they don't have the 510K. And so just be aware, legally you should be using a 510K approved material. Others that you can, materials that you can use with your CAD/CAM system, implant guides, drill guides. So again, as long as you're using an approved material, there's getting to be more and more really good, and they're usually along the line of PMMA or the acryl polymers. The other are millable composite, hybrid composite materials. An example would be Anamic from Vita, and it basically has a ceramic backbone infused with an acryl polymer. And so what is unique about it is that it's millable, that once it's milled, you can clean it up, polish it, you can stain it, dye it, color it. You don't have to fire it. You don't have to center it. And it has the strength of a composite and plus some. So it's not as strong as zirconia, but it's for a long-term restoration. And I think we're going to see more materials along this line as we start to tap into the potential of CAD/CAM. It's going to open up a whole new line of materials that we could use for restorative. And the other, like the Anamic, from what I understand, is actually, even though it's just now coming out to market, it's near the end of its patent. So I wouldn't be surprised within the next few years that we'll see a number of materials that provide that same benefit or service. All right, now I'm about to wrap up. I want to let everybody know that on October 10th and 11th here in Louisville, Kentucky, we're going to have a digital forum. This will be our second one. We did it here in Louisville. We've done it around the U.S. at various shows, but we did our initial one here in Louisville. And basically, if you're really looking at getting into CAD/CAM, this is an excellent opportunity to kind of see all sides of it. We've got Mark Jackson, Chunk Yankner, Alf Lastry, and others. And what they're going to do is talk about, here's how you can use it, and here's the different markets, etc., that you can get into. Chuck Yankner for can you justify it? Will your business justify the investment? And what will it take to buy into this, financially? Is it worth it for you? And it may not be, or it may be, but he just really, in a non-committal way, helps you through that process of doing that analysis. And then also what's coming in the future. And and others to discuss, I think we just got him on board, is that Dr. Russell Giordano. And again, he is one of the leading experts in the U.S., if not the world, in zirconia material science. So, and he's an excellent presenter as well. So if you get a chance, please come to Louisville, Kentucky. And as you can see at the bottom, visit whipmix.com or call a number for details. And with that, I'm open to Q&A.
All right, thanks, Brian. We do have one question, and it was, what was the name of the powder to ask the manufacturer?
Okay, well, is your zirconia powder, what is your source? And the common is Toso, and that's made out of Japan. And if it's not Toso, then you may want to dig a little bit and find out who. Again, I know there's a major European zirconia disc manufacturer that's using a source out of China, and again, I think they make a quality product. But if they're not using Toso, you may, I would just put a little question mark there. Again, not saying that they're bad, but I'd put a question mark.
All right, and so far that's the only question we had. Just a couple reminders. In 48 hours, you'll get the information required for your NBC credit. And if you have any other questions, shoot us an email at webinar@whipmix.com. Oh, now we have that's it. Looks like those are all the questions. Have a great day, everybody. Thank you, Brian.
Bye.